I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
This week, how could pandemics happen? What's nanotechnology all about? And what's the most toxic chemical anyone ever dreamed up? It is Q&A time. We have a panel of scientists who are taking on the science questions you've been sending in. Hello, I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
Let me introduce the fine panel of people who are going to be answering your questions for you this week. Carolyn Crawford, she's from the University of Cambridge, and she's at the end of the scale which looks at things that are extremely big because you're a space scientist.
That's right, yes.
So we're going to talk about the universe. Sitting next to Carolyn, Colm Durkin, who's also from Cambridge University, and he's concerned with the extremely small. I'm intrigued. Down as small as what?
Small as you can get.
How big's that?
Just about the size of atoms and a bit bigger.
Pretty small.
So, pretty small.
I'll hand you that. Thank you, Colm. And Hayden Belfield, a newbie on the programme as well. Welcome to the show. You're from the Centre for Existential Risk. What does that mean and what does that involve?
So these are really big threats to international security. So things like a pandemic or a nuclear war or other happy things like that.
And you calculate or look at the likelihood of those things happening and what ways to mitigate them and so on?
Yeah, very much looking at ways to try and stop them because nobody wants that to happen.
Thank you very much, Hayden. And also here is Liliana Fruck, who's a chemist at the University of Cambridge and also a keen cook. Soon to be restaurateur.
Yes. Yeah? And fortunately, there are no big extremes in being a cook.
Only cooking.
Extreme of pleasure. Yeah.
Extreme taste.
Yes,
surely.
exactly.
Now, everyone's got a bit of a myth to bust for us, haven't you? What's your myth then, Liliana?
Well, I was recently asked about dopamine because I work with dopamine. Dopamine is a hormone that is usually related to all pleasurable things. So people think that this is the hormone of pleasure, but actually it's a hormone of motivation. Very important for learning.
Of course, when one eats some delicious food,
yes,
you are motivated to seek more of the same.
Exactly.
So you will get a rush of dopamine in your brain.
Yes. So it's a motivational hormone, but then you have all kinds of other chemicals which are related of keeping this happiness high.
And from very high to very low, very, very small, Colm, there must be myths abounding in the nano world.
Oh, there are more than you can shake a stick at, Chris. The one that really irks me is people have been saying for about 20 years that nanotechnologists will be able to make what they call nanorobots that can go around the body repairing damaged cells, and that is just complete twaddle. I'm afraid.
Why?
You basically cannot make things that do what you want at those length scales. You just can't. You can't make a little robot that can move around to any part of the body at will and repair cells. We can do things that are pretty cool and that are close, but not quite that. Not an autonomous machine.
Does anyone else feel saddened to hear that?
I know. It's sorry to shatter your dreams.
I wanted to introduce Carolyn's myth as well, because you must have some massive myths with the universe at your fingertips.
Yes, but I'm just going to return to an old chestnut, having had this reflected back at me when I was talking to some school children this week, which is when they think of astronauts floating around in space, I keep getting told there's no gravity in space, and that's why they're floating. And I just want to remind people there's plenty of gravity everywhere in space. And, you know, astronauts aren't that far away if they're in the International Space Station. They're only 400 or 500 kilometres further out. So, yeah, they've got reduced gravity, but it's only reduced to 90% of what we have on Earth. So the point is that they're in free fall. They're sitting in an International Space Station that is falling at the same rate as the astronauts around Earth. So there's no kind of reaction force between the two, and that's why they're weightless. So there's plenty of gravity in space.
I must admit, I used to find that quite tricky to understand until actually I met Dave Ansell, who we're going to hear from later on in the programme, who showed me, or introduced me to the experiment that Isaac Newton did, or his thought experiment about firing a gun and firing a gun harder and harder, and the bullet goes further and further but falls under gravity, and eventually it's going so fast that it's falling towards the Earth all the time and missing the Earth's surface. And as a result, it's in orbit. And then I suddenly understood, now I understand how it's under the influence of gravity, it's always falling, and falling and missing.
Yeah, that's exactly what an orbit is. You're just falling towards something. It's just like it's deflecting your route and just sort of continually curving you around, but you're not being pulled onto something.
Thank you, Carolyn. And Hayden, what have you got for us in the myths department?
So the myth I thought I could talk about today was that we should be scared of the Terminator. The things we have to be worried about, the real risks aren't to do with some unstoppable, evil robot thing that's marching towards you and has two hands and scary red eyes. The real risk is that our artificial intelligence, AI systems are not smart, that they break in many different ways, that they have like big accidents, or that they get misused by sort of bad actors. It's not that this one evil red-eyed thing is out to get you.
There are far more ways to do evil and be evil than just building a robot to do it for you. Absolutely. Thank you very much. Now, if you'd like to get in touch with the programme and ask us any questions, you can email chris@thenakedscientist.com or tweet @nakedscientist. That's exactly what Les has done, who's calling from over. Les, hello, welcome to the programme. What would you like to ask us?
Is an atom always the same size with something as dense as gold or as gaseous as helium?
Sure. Well, this sounds like one for Com to answer. How big are atoms? Les is saying, are they all the same size? Presumably not.
So, Les, all atoms of the same material are the same size, but different atoms of different materials are different sizes. So, for instance, the smallest atom is hydrogen, and a single atom of hydrogen is about 1/20th of a nanometer across.
So how big is a nanometer?
So a nanometer is 1/1000th of a meter. So to give you an example, if you take a hair, so a hair is about 50,000 nanometers across. The distance between atoms in a typical material is about 1/4 of a nanometer. And the size of a hydrogen atom is about 1/20th of a nanometer. Then if you go up to something like, you mentioned gold. So gold is about, it's about 1/10th of a nanometer is its outer radius. But all gold atoms are the same, all hydrogen atoms are the same.
So in summary then, all atoms of a type or one specific element
Yes.
are the same size, but because there are nearly 120 different elements, there's 120 atoms of different sizes
That's right.
to choose from.
Yeah.
Les, thanks very much for your call, and Com, thanks very much for the answer. Now, before we dive into any more questions, for those of you at home, we've got a little Guess Who quiz running through the programme. We'll scatter the clues across the hour for you to guess at, but here's your first one. Clue 1, this North American creature can live for up to 15 years. I think you agree that does leave the field open quite a bit, but what do you think it might be? Question for you, Carolyn. This one actually says, to try and get some sense of scale, how big is the Earth in the grand scheme of things?
Tiny, just about insignificant. That's the short answer. It depends what you mean by big. If you meant in terms of size, the diameter of the Earth, well, it's 12,740 kilometres across, which means that you could pack about 1,000 Earths inside Jupiter, maybe 1 million Earths inside the Sun. We are truly insignificant. And in terms of mass, it's not much better. The mass of the Earth, it's sort of 1/300th of the mass of Jupiter, 1/300,000th of the mass of the Sun. So the Earth is tiny, whether you think in size or mass, and I'm afraid we are truly insignificant.
Talking of things that are not insignificant, though, the moon is a very big presence in our sky. And I watched a really interesting documentary, and it taught me something the other day. I hadn't realised this, which is that the side of the moon that faces the Earth is completely different from the side of the moon that faces out into space in terms of its surface appearance.
That's right. The side of the moon towards the Earth has a lot of those dark, we call them seas or maria, but they're actually just flat
splodges, what we call man in the moon type pictures.
Yeah, or they describe the bunny rabbit in the moon, if you see that. But the far side of the moon's only got one of those large mare or seas, and most of it is the much lighter weight sort of cratered terrain. So there's a big difference between the two sides.
So it really is a dark side of the moon in terms of its mysteriousness. Thanks very much for that.
Well, actually, it's a lighter side of the moon because it has fewer of the seas.
And that's true, and it gets more sunshine, of course.
Yes, it does, yeah.
It's odd because you'd expect, I would always have imagined that the side of the moon that faces the Earth would have been more protected from collisions.
Well, that's certainly true. You get moons around Saturn, for example. I think it's QnA, which one side is far more cratered than the other side. And the explanation for that is they think it's gone through a 180-degree twist in its history. And so one side was a lot more pockmarked by meteors, and then it got turned round, and it's got this weird dichotomy of its surfaces. I don't think that's the case for the moon.
Thank you very much to both of you. Hayden, we've got this question which has come in, which is how could a pandemic happen? That must be presumably something that you look at the Centre for Existential Risk, because that really is a massive planet-scale risk, isn't it, to our future?
Yeah, that's right. So a pandemic is a really big disease, so a disease that would get everywhere in the world and infect a big percentage of the entire sort of world's population. So 100 years ago, we had our last sort of really big pandemic, the Spanish flu. That killed more people, actually, than World War I, which had just came afterwards, and World War II combined. So it killed between 50 and 100 million people, so really devastating, and yet not as well known as World War I and World War II for some reason. And then more recently, people will be familiar with things like Ebola or SARS or the swine flu, bird flu. Lots of these things were animal diseases that hopped over into humans and sort of caused a lot of trouble. But that's not as bad as it could get, right? Ebola hasn't killed, thankfully, that many people. Lots of doctors are agreed that we're due a big pandemic flu that will affect lots and lots of people like it did 100 years ago.
Why do they think that?
It's just happened very regularly throughout human history. And though we might be better placed in some respects nowadays, we all know to wash our hands and to sneeze into our arms and things like that. On the other hand, we're much more interconnected. So if somebody ill gets on a plane in Heathrow, they can be anywhere in the world in sort of a few hours. One thing that we're particularly worried about is not just a natural pandemic, so a pandemic hopping over from another species, but someone cooking up a far nastier pandemic. There's some risk that something might escape from the lab or be deliberately made and released into the world. What we can do, nevertheless, is we can put in place various measures to try and reduce the risk. So better biosurveillance around the world, or better regulation of what is allowed to be published or what things you're allowed to order online.
Thanks, Hayden. Now, Liliana, this one takes us in a totally different direction. What's the smelliest chemical, wonders this person? What a stinker.
Well, there are many contenders, but no matter which molecule we take, it will definitely contain some thiols. So thiols are sulfur compounds. And there are two contenders. One is thioacetone. So it's a very small molecule that has a sulfur in its structure. And the other one are mercaptans, which also have thiols. And they're the smelliest compounds. So first time when thioacetone was made at the end of 19th century, people had induced vomiting and they feel nauseous.
What, when they smelled it?
Yes, in the range 1 kilometer around the chemical facility where this was made. So it's extremely potent and smelly compound. And skunks, for example, have lots of thiolated
They make methylmercaptan, don't they? Because
yes.
it's similar to the stuff that asparagus gets metabolized to.
Yes.
When you eat asparagus and have asparagus wee.
It's the same chemical. And the problem with thiols is they are actually the products of decomposition of proteins. So you will find them in cadavers or in all these non-appetizing things. And so we are evolutionary primed to feel a little bit kind of...
Steer clear of this. It could be bad for you.
Steer clear of that. And there are some other compounds which don't have thiols. For example, lots of amines can be also
fishy
very smelly,
smells,
fishy smells. And one of the worst that I worked with was cadaverine. Yeah, the name says it's a product of
smells
cadaver.
like corpses.
Yes.
Yeah.
You use it in chemical synthesis because it's very useful to make some amines. And when you use it, you can't get rid of the smell. So you get out of the lab and people just steer away from you. And you get used to it already. So
well, I remember
fun.
I worked in a lab once where we would add one of these particular sulfur compounds to gels that we were running when we were studying proteins.
Yes.
And the lab head would come in and sort of sniff and go, it smells like all brand research laboratories in here today. Because it does smell like someone's had a very bad bout of flatulence, doesn't it? Really, really unpleasant.
And what is really curious, then again, we also have lots of food stuff that is smelly and we like. Just imagine some of the French cheeses or this fruit, durian. I don't know if you ever tried
the
that.
Durian, yes, it's actually banned from taking it indoors in some place like in Singapore. You're not allowed to take that inside because it's a weapon. Effectively, empties a residence faster.
Absolutely.
But it tastes fantastic though, when you actually eat the flesh.
And so this was, some neurologists were actually exploring this. Why these things which we are evolutionary primed not to like still taste so well. And they found something which is called the backward smelling reflex. That means first you basically smell and you have this nauseous feeling, but then you activate some receptors which give you a huge amount of pleasure. So, there is a balance. Yes.
Thank you very much, Liliana. We're answering your science questions, of course, but we're also going to tell you now about an experiment we're going to do at the end of the month. This is great fun. You've probably heard the claim, in space, no one can hear you scream. Well, someone got in touch with me recently and said, we've got hold of a large balloon that we're going to send to the edge of space. Would you like to be part of it? And I thought, this sounds like a wonderful opportunity to do an experiment. So Dave Ansell, who's been a long-term member of the Naked Scientists, also teamed up. And the guy who got in touch with me in the first place is Omar. And how do you happen to be in charge of a helium balloon going to space?
I actually am very passionate about electronics and how they've advanced over the years. And the thing that made me want to do this the first time was exposing, these types of electronics that you can actually buy anywhere to harsh environments such as space, and see how they fare. I think that is a very good indicator of how well we've progressed in the side of electrical engineering and electronics in general.
So you thought you'd get in touch to see if we wanted to come on your balloon with you? So let everyone in on the secret, what we decided to do. I suggested to Omar, we know you've heard this claim, no one can hear you scream in space, but actually we could test the physics of this, of how sound is transmitted through a gas, and actually work out whether or not, as the gas gets thinner with altitude, the sound does disappear. Then we thought, how do we actually test this, which is where Dave got involved. So what did you think when you heard us saying we're going to try and do this? What first went through your mind? Oh my goodness, it's that Chris Smith again.
That was part of it. But so basically we need a way of producing sound and a way of recording that sound. I did have a long diversion into trying to produce horns of various different types to take up into space. But we ended up, let's go for the simple thing. We've got a loudspeaker and a microphone. You play something, it could be your scream. So if you want to send us in a scream, you can get it up and played in space.
Well, actually, Dave, Mark Litton sent me one yesterday. Would you like to hear Mark's scream? This is what he would like us to send into near space for him. I'll see if I can get this to play. Woo-hoo! So that's Mark's contribution to our effort. And actually, Sue Marchant then heard that we were doing this, Sue Marchant from the BBC Eastern region, and she said, well, I want to be part of this, and so she's done us a scream. You better hold on to your hats for Sue's scream. Here it is.
Oh, did you hear that? Ow! Did you hear that? Ow! I bet you heard that.
So there you go. So we've got a range of screams we could put on there, and you've done some as well.
Sue's is particularly nice. We've got a range of volumes, yes. So if we do pick the volume wrong...
But tell us about the apparatus, first of all, that you've designed, because the key thing here is if we just put a speaker in a box, then the vibrations could come out of the speaker, transmit through the box to the microphone, which is also stuck on the box, and then it would just cheat, and that wouldn't test sound transmission through air. So what have you done to get around that?
So basically, we've tried to isolate both the microphone and the loudspeaker from the box. Oh, they hear the speaker. It's Omar's screen, in fact, which we've been testing it with.
He's just plugged it in. So basically, we've isolated the microphone and the speaker so we know the sound can only go through the gas.
So they're both hanging on springs to damp out any resonances you make on those springs.
Dave's put a picture of this on the internet. There's also a video of this. So, Omar, you've written the software, because we're sending a computer to do this, because we're actually going to do it properly in every increment of altitude. We're going to make a recording, right?
Yes. This was just part of the test script, making it run every 5 seconds. But in the real scenario, we're probably going to make it run every 5 minutes. So on here as well, we have a GPS tracker as well as a pressure sensor.
Yep.
And that will be able to also calculate the altitude. And then we'll be able to feed that information into the main microcontroller. That will then couple, the sound that we recorded with how high it was when
So we're going to basically be able to plot a graph of how loud it is with increasing altitude, and we'll see, therefore we can relay that to pressure, and we can see how the sound is going to change if it does. You're using a Raspberry Pi computer to do all this. How do you know it'll survive at 3,000ths of the pressure you get at the surface? Exactly. David, how can we mitigate against that?
So I've got a vacuum pump in my shed, as you do.
Yeah.
It's not a perfect vacuum pump, it won't get quite that low, but I've pumped it down to maybe 70, 80 millibar, and everything seems to work fine. So
you've got the rig there with the mechanically decoupled microphone and speaker and the Raspberry Pi stock on the outside. You put that in a vacuum chamber, and you had Omar's screams running through it.
Yeah. So
is that what you said? Because you sent me the audio this afternoon. Is that what you sent me?
That's what I sent. Yes.
Because I've got your 2 test runs here, so I can play. This is this one. You can talk us through what we're hearing. Here's the first one that you sent me.
So that is probably at the full atmosphere.
That's at ground level.
Yeah.
And then this was the second one you sent me.
So you can hear the air being pumped out, but it's at a much lower pressure, and you should be able to hear it's much quieter as well.
Yeah, it was a much more threadbare scream, and that's not because your apparatus is falling to pieces.
Hopefully not. It should be that there's just basically less air there. So as the loudspeaker moves, it moves less air. So there's less air moving inside the box. So you get less forces on the microphone.
And of course, we're recording all of this on the way up. And then the balloon gets to 120,000 feet. How do we get the balloon back?
Because there's less air pressure there, the helium in the balloon will force the balloon to actually expand and expand and expand until it pops and, falls back down to Earth.
And how do we know where it's going to come down?
So we have a receiver on the ground and a transmitter up in the box on the balloon.
Because I want my computer back.
Obviously, we'd be able to use that information to actually literally chase it using with a car.
Super. When's the balloon going up?
29th of June.
It's definitely going to be then, is it? We're going to do it then?
Yes, most likely then. I keep checking the weather every day to make sure that the weather is as good as possible for the launch, and it does seem that it will be that day.
The worry is that if the wind direction's in the wrong direction, it ends up in the middle of the sea, and then we don't get any data back at all.
Let's hope that doesn't happen. It doesn't end up in the Bristol Channel. Thank you both very much for coming in and telling us about it. So if you want to be part of our experiment, you can send in your screams. Best scream gets a broadcast here, but we'll put it on the machine, and on its way up it'll play it, we'll record it, and you can hear yourself scream in near space. Dave Ansell and Omar Gad, thank you very much indeed for coming in and telling us all about it. But in the meantime, we've got a question for you, Colm, which has actually come in from Deirdre.
I've heard of nanotechnology, but what does it mean?
So what is it? Please reveal. What is nanotechnology?
Okay, thanks, Deirdre. So how long have you got? Nanotechnology is... I'm going to give you the formal definition and then tell you what that actually means, because we scientists love complicated ways of saying really simple things. Basically, nanotechnology is the ability to both make and characterize and use things that have nanometer dimensions. A nanometer is 1/1000th of a meter. And what happens is, the reason why nanotechnology exists as a field is that when you have any piece of material that's got those sort of dimensions that you can measure in nanometers, then its properties become different to larger bits of the same material. Simplest example, if you've ever looked at a stained glass window, you'll see all these different colours in it, and in many cases those colours are all made using the same material, which is gold. Artists in medieval times did all sorts of experiments where they fiddle around with all sorts of chemicals because they had nice colours, and they realised that just by changing the way in which they mixed certain chemicals together, they could change the colour just by basically waiting for a little bit longer. So for instance, gold, when it's in nanoparticle form, so when it's a few nanometers across, a lump of gold is no longer gold in colour. It can be anywhere from green, red, blue, yellow, take your pick, and it's purely down to its size. And that's just one example of about 100 that I could give you.
Oh, Liliana, go for it.
Yeah, I wanted to ask you said colours are changing. What else changes when you go the nanos,
Sure.
conductivity or something else?
Yeah. So what we do in my lab is, we try to understand why the properties of materials change, and then we make them do what we want, and then we try and do something useful with it. So the sort of things that change are electrical properties. If you take gold as an example, it does so many things. It's a really good conductor of heat and electricity. If you make it small enough, as in nanometer size, then it can become an insulator. So you've got colour, chemical properties change, electrical properties change, and so on.
Cool. Thank you very much. You're listening to The Naked Scientists with me, Chris Smith. And this week, we're answering the science questions you've been sending us. Helping me to do that are physicist Colm Durkin, space scientist Carolyn Crawford, Hayden Belfield from the Centre for Existential Risk, who looks at the major challenges facing the planet, and also Liliana Frooke, who's from Cambridge University, and she looks at extreme chemistry. Now, if you want to send in a question to us for a programme like this in future, you can email chris@thenakedscientist.com. You can also tweet @nakedscientists. You can also send questions to us via our Facebook page. You look up The Naked Scientists on Facebook and we'll be there. We've also got a game of Guess Who running through the programme. We heard first that our mystery guest or animal has a lifespan of about 15 years and it lives in the waters of North America. Here's your second clue. Its name translates to water dog or water servant. Any ideas? Don't worry if not, more clues are coming up later. Now, we always try and do a little quiz for our panel of people when we do this, and they're competing for a prize beyond price, which is the Naked Scientist Big Brain of the Week award. And there are 3 rounds, and because this is our extreme month, where we have a series of programmes dominated by the theme of extreme things, this is an extreme Q&A show, and so this has some kind of relevance to this quiz where everything's to do with extremes. So our two teams are Colm and Carolyn and Hayden and Liliana. Round 1 is extreme weather. Are you ready, both of you? You may confer. This first question, the most rain recorded to fall in 1 minute was 100 millimetres. Is that a science fact or a science fiction?
Gosh. Feels like we've had most of that over the last week, actually. So, should we say fact?
I would say that that's possible in places in India, yeah.
I'm really sorry. Actually, it's false. The most rain to fall in a minute was 31.2 millimetres. That's 1.23 inches. It was recorded in 1956 on the 4th of July at Unionville in Maryland, in America. Okay, unfortunately, 0 for you. Hayden and Liliana, see if you can improve on the score of 0. The coldest temperature ever recorded on Earth was minus 60.3 degrees C. Is that a science fact or a science fiction? What do you think?
I would say it's a fact.
Minus
I think
60.
it was even more than minus 60.
Well, can't we get things incredibly cold in the lab? So couldn't it be even
just
lower?
to clarify, this is naturally like in the natural world.
But good thinking.
I was thinking, because it's the extreme month, that it might be extremely hard or extremely tricky questions.
I would say it's a fact. It can get pretty cold, but I don't know. You are extreme risk.
I'm going to go with you.
You're going science fact?
Yeah. No.
Okay, level pegging on 0. The coldest temperature recorded was even colder than the minus 60.3. It was minus 89.2 degrees C, minus 128.5 degrees Fahrenheit. That was recorded in July 1983 in Vostok, Antarctica. Right, back to Colm and Carolyn. See if you can improve on your score. This is round 2, extreme fact or extreme fantasy. This is an example of someone who's extremely dedicated. The Schmidt pain scale was created by allowing venomous things to sting and bite people and then record their reactions. Is that a science fact or is that something I made up?
Ooh.
I think that's correct.
Oh, you think it's correct? I was going to say it's fantasy. Well, I'm happy to go with Colm's decision here. Hey, that was the right decision on my half. Good. Excellent. Well done.
Yes, you were right, Carolyn. That's right. Right to listen. It's true. In 1983, entomologist Justin Schmidt famously came up with his Schmidt pain index. He rates the pain of various insect stings and bites by letting them sting him. For each, he also provides a nice colourful description. So rated 2 on his pain index is a wasp sting. That causes a pain that he says is hot and smoky, almost irreverent. Imagine W.C. Fields extinguishing a cigar on your tongue, he says. Level 4 is apparently the top of the scale, although Schmidt says the pain from a Nicaraguan bullet ant is 4+, and it's like walking over flaming charcoal with a 3-inch nail embedded in your foot. Anyone here any painful brushes with nature? Anybody?
Well, I had a wasp sting. Yeah, it wasn't.
But that's Schmidt scale too.
I know, but it didn't feel like this. He was very poetic.
It's very poetic or potent. I got stung by a Portuguese man of war jellyfish. That was pretty painful. I have to say, I noticed that. I won't be repeating the experience either. Right, so you've got 1 point so far. So Carolyn and Colm go into the lead, score of 1. Over to Liliana and to Hayden. Here you go. This is your question. An example of someone who's extremely dedicated. Greenland's only railway was built to move a meteorite. Science fact or science fantasy?
This is so crazy that it's probably a fact.
Greenland's only railway.
Or did I make that up?
Well, I like that.
Yeah,
I mean, it's true.
You would expect meteorites falling into some really deserted places, and then
I'm presuming it's so big that they needed to move it to the coast or something like that.
Yeah, what are you going for?
I could.
Let's.
Carolyn is looking very.
She knows. She knows.
Yeah.
What
fact or fiction?
Fact.
I think fact. Yeah. Yeah. Okay.
Carolyn sounds like she knows more about it than I do, but I'll read you what's written here. It's Arctic explorer Robert Peary who located a 31-ton lump of metal that local Inuit had been using as a source of iron for their harpoons and knives. It was the third largest iron-rich meteorite recorded on Earth. He sold it for $40,000 to a museum in New York, but first he had to get it on a ship to get it there. Unfortunately, it was nowhere near where the ship was, so the only way to get it to where he could dock a boat was to build a railroad to put the meteorite on there and then move this 3.4 by 2.1 by 1.7 metre chunk of iron to the ship, and it's now called the Cape York meteorite.
And I can tell you he was full of dopamine because he had a huge
well, he got
motivation.
trousered $40,000. I suspect it was a lot of money in those days, wasn't it?
Well.
OK, one each, level pegging. Into round 3, extremely trivial. Coleman Carolyn, extremely stupid is your question. Ostriches' eyes are bigger than their brains. Science fact or science fiction?
Ooh, I suspect that.
I like that.
So you've got to try and second guess. It's not the answer you expect.
No, I mean, I would expect
think it's fiction, but...
It's funny. Okay, I would expect it's true because they're really quite stupid and they have big eyes.
But I'm just wondering if it's a double bluff because we expect it to be true. It's actually
that's too clever
not.
for me.
Oh, sorry.
So what are you going to go true at? Science fact or science fiction?
I'll listen to you this time.
Oh dear. Well, I'm saying it's fiction. So if we fail, I'm sorry, Cole.
No.
Oh no.
Actually, this is true. An ostrich brain, thanks to a Turkish publication I found. I checked the diameter and the various measurements. The dimensions are 6 centimetres by 4 centimetres by 4 centimetres. So the volume of the brain is about 96 cubic centimetres. The eyes are actually 4 centimetres diameter. So the volume of a sphere being 4/3 pi r cubed, that means the volume of the eye is more than the volume of the brain. It's about 125 to or so cubic centimetres each eye. And they've got 2 of those. So most of an ostrich's head is actually its eyeballs. There's very little brain there. They're allegedly endowed with these enormous eyes in order to be able to see well in the dark so they can escape predators. They're not very good at that, though, because when something does frighten them, they just run around in circles. So actually they can see what's going to kill them very well, but they're not very good at escaping. They are very fast, though, so there is that. Right, it's all on this one, you two. OK, if you get this, then we don't have to go to a tiebreaker. Are you ready?
Yes.
OK, you're going to have to give your answer quickly to this one. Okay. Stewardess is the longest word you can type with only one hand on a keyboard with the same hand.
What about stewardesses? Surely you must be able to do that with one hand.
I'll leave it to you.
I think it's not true because you can do stewardesses.
That was my sneaky one. Indeed, stewardesses is the longest word that you can type with only one hand. All those letters are on the left-hand side of the keyboard. The E is sneakily there as well. So stewardess, yes, you can type that, but stewardesses is up for grabs, and that's the longest one you can do with one hand. Bonus point then, can you tell me what is the longest word you can type with just one row of a computer keyboard? What do you think?
QWERTY. What would that be?
Oh, no, it's got to be in the dictionary.
Correct my own word.
I'll let you out of your misery. It's typewriter. Isn't that appropriate?
It's
all on the top line of the keyboard. Well done. Our Big Brains of the Week award goes to Liliana and Hayden. Very well done. Give them a round of applause. Very well done.
Wow.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
You are indeed listening to The Naked Scientists with me, Chris Smith, and this week we're answering the science questions you've been sending us. Still to come, how bad could climate change get? And what's the biggest star that anyone's ever discovered? Before that, though, time for a question from you, Liliana. We want to know, what is the most toxic chemical that's ever been described?
Interesting. Again, plenty of candidates, but the most toxic chemical is basically a natural product. There are some chemicals which were made in the lab, which can be very tricky, but the most toxic, according to some scales, is the botulinum toxin, which is, funnily enough, used in Botox. But there is a particular scale which is used, and this is a lethal dosage that kills 50% of subjects. And this is, in the case of botulinum toxic, 1 nanogram per kilogram. That means that you need very low amounts to cause really toxic effects. So it's kind of, it's a little bit ironic that you can basically use it also in cosmetics today. When we think about synthetic compounds, there are some neurotoxins that have been made. And, when Hayden was talking about some dangerous stuff and some risks. So there have been lots of chemicals that have been made that are extremely toxic. One of the most toxic ones is the chemical called VX. It's a synthetic poison nerve agent, so it basically inhibits signaling between the nerves. It will cause lots of muscles convulsions and heart attack, and it will really kill people instantaneously. It's still less toxic than botulinum, so you would need around 3 micrograms of this compound to kill the person, which means nature has made the most toxic ones.
I've got something I think can challenge that, Liliana. I said that someone had got in touch, and I think that this lady's cooked up something that could give you a run for your money. I just want to read you this letter, and you can, as the chemist on the team, you can tell us what you think of this. So this is from Mrs. E. Norton, and she's written in, and she says she likes the programme, but she's also a fan of cooking, and she was making some stock. She was boiling up some lamb bones in 3 independent pots. She didn't have a lid for one of them, so she found instead a frying pan that was a bit smaller than the top surface of the saucepan, put 2 wooden skewers across so that the steam could still escape, and put the frying pan bottom down on top of the pot, because the frying pan was slightly smaller than the diameter of the cooking pot. So that way it acted as a lid, but it was a frying pan. She went away for a couple of hours, leaving her stock simmering, came back having done some other jobs, and she said after 2 hours of boiling, the other pots had this lovely honey-coloured stock in them, delicious. The pot with the frying pan on the top now had this charcoal black or dark green substance. The pan was black on its bottom, although it did wash up fine later, I'm pleased to hear. She says she's kept this liquid separate. Should I use it? She's wondering, or should I chuck it away?
Well, considering that there is a control experiment that she has done, and this is this honey-coloured wonderful stock, I would say probably chuck it away. What I'm suspecting...
What do you think's in it?
Yeah, so I'm suspecting that the pan was made of copper.
She said it was copper-bottomed pot.
So it's probably copper hydroxide or copper carbonate.
But why did it come off?
That means the copper oxidized. So copper pan is made of metallic copper. Copper very easily oxidizes. So I think the combination of steam and combination of maybe some herbs that she has put and some aromatic compounds that were boiling oxidized the copper, made copper 2 compounds, carbonate or hydroxide. They are not cases of direct poisoning with the copper 2 compounds, but there is a certain lethal dose there. But everybody is more or less sensitive to some of the copper ions, so I would just say chuck it away.
Probably good advice. It probably wouldn't taste that good, and it doesn't look that good either compared to what else is on the plate.
Yeah, there is the interesting thing about food. Usually it does look very good and tasty, and then you should eat it.
Yeah, if it doesn't, you shouldn't.
Then think twice.
Absolutely. Thanks very much for that, Liliana. So there you go. Throw that stock away. Keep the stuff that does look good. Hayden, one for you.
How bad could climate change get?
So this is an existential risk, isn't it? The threat posed by climate change. What does the Centre for Existential Risk think about that, and how are you trying to plan for it?
Yeah, so this will be something that people are really familiar with, I'm sure, for over the last few months of the Extinction Rebellion protests and people like Greta Thunberg really raising alarm about this issue. The simplest answer is we don't really know, but that's something to be worried about. We know that the definite effects of climate change are going to be really catastrophic for people around the world. And there's a moral element to it in that the people who have contributed the least, who have burnt the least amount of stuff, are going to suffer the worst consequences. So we should do something even on the most likely outcome. But what climate scientists do, what they look at is they model different scenarios. And the IPCC, the Intergovernmental Panel on Climate Change that people will be familiar with, gathers all these together and looks at what are the most likely outcomes of different scenarios. So if we pump this amount of carbon dioxide into the atmosphere, will we get this amount of heating? What might the effects of that be? But the problem is that they mostly look at sort of the most realistic outcomes. They don't pay as much attention to sort of the very unlikely outcomes of 5 degrees or over. And if we were very unlucky, we hit a few bad feedback loops. So that's things like permafrost up in the Arctic melts and releases a whole load of methane, a much more powerful greenhouse gas. You might get sort of much more warming than you might expect. So the worry is for something greater than 5 degrees that it might be very bad indeed. It might affect the ecosystems that we rely on. So that's the sort of natural world that produce clean water and pollination and things like that for us. It might affect our ability to grow food or to have clean water, and it might spark conflicts. So the Syrian war and Sudanese war have often said they were the world's first climate conflicts. So the worry is that if we are very unlucky and we have sort of very runaway climate change of over 5 degrees of warming, that you get huge amounts of people having to move because they literally can't live where they used to live.
And, the world is becoming more and more populous, isn't it? There's 7.5 billion people on it now and growing at 1% per year or thereabouts, which actually is a doubling every 75 years or so. So we could be looking at huge numbers of people in not too long a time. Now, Carolyn, here's a question for you, which has come in from Ankita.
What's the biggest star and what's it like?
What do you think about that one?
taking biggest to mean size, now we're talking diameter of stars, the most reliable estimate I can give you is a star that's just short of 4,000 light years away. It's a red supergiant called VY Canis Majoris. And its diameter is somewhere between about 1,400 to 2,000 times the diameter of the Sun, which means its volume is 3 billion times the volume of the Sun. And, these are all large numbers. But
it's a big star. That could give Justin Bieber a run for his money.
Well, if you work out that if you travelled round its circumference at the speed of light, it would take you 6 hours to go once round. Whereas if you did the same thing with our Sun, it would just take you 145 seconds. Now, so that's a lot bigger, but there is an interesting question here, is how do we know the diameter of this star? Because even when you look through telescope, most stars just look like points. A star like this that's big and relatively near, you can sometimes resolve the disk, and you measure the angular size of the disk, you know how far away the star is, you've got a triangle and you can measure the width of the disk. But once further away, you can't actually see the disk, and you have to be quite clever, so you have to do some physics to infer it for most of the stars. So even though there could be some stars which may be larger, the most reliable estimate is the VY Canis Majoris at the minute.
Still, that's a pretty big star, isn't it? Thanks, Carolyn, very much. Hayden, back here on Earth, what is the doomsday clock, wonders this person, and what does that actually mean?
I love the doomsday clock. I think it's a great, great symbol of our impending doom or what we can do about it. So
You're an optimist, aren't you?
Yeah. So the doomsday clock is a clock with the hour hand on 12 midnight and then the minute hand sort of showing, is it 15 minutes to midnight? Is it 10 minutes to midnight? Where if it's on midnight, then everything's gone very badly indeed. So it was set up by something called the Bulletin of Atomic Scientists, who were a group of people who worked on the bomb in the Second World War and felt pretty bad about what they'd brought into existence. So Oppenheimer famously said after the first atomic bomb test, "I am become death, the destroyer of worlds." They were feeling pretty bad about what they did. They thought they should warn people about the dangers of this new weapon. So they created this great visual representation of risk. And they've been doing it for the last 70 years. So it was the closest it's ever been to midnight, 2 minutes to midnight, in 1953, when the first really big new type of nuclear weapon, the thermonuclear weapon, was exploded. And then it was very close, of course, again in the Cuban Missile Crisis, very close again in the early 80s. But then at the end of the Cold War, it was put back over 10 minutes because things were getting safer. There was a reduction in tension. But then over the last couple of decades, they've added in other threats to the world. So things like climate change and things like new technologies. So I've got a question for you. What do you think the time currently is?
5 to 12? 10 to 12? I think climate change coupled with human population expansion is a huge risk. I'd say it's 5 to 12. What do you think, Liliana?
I'm a little bit more optimistic, so I will go 11 to 12.
Unfortunately, it's much worse than both of you think. It's currently set at 2 minutes to midnight, which is the joint closest with 1953 that it's ever been.
And is that attributable to the risks I'm suggesting, things like population, climate change and so on?
Yes. And is it also accounting for new technologies that could help us to resolve this?
Yeah, so they try and, it's not exactly a strictly scientific thing, but they try and to account for all of those things. So it's because of our new biotechnology, things to do with artificial intelligence, machine learning, but mostly it's been driven over the last few years by how things have gone worse in the nuclear zone. So it was set at 2 minutes to midnight last year, and then this year they didn't move it any closer to midnight, but they didn't want to say everything's fine, everything's holding steady. So they've described it as the new abnormal. So we're currently living in the new abnormal and desperately need to get that minute hand further away from midnight.
We desperately do. Hayden, thank you so much. This is The Naked Scientists with me, Chris Smith, and we've also got a game of Guess Who running during the programme. I told you, first of all, that our mystery guest creature lives for about 15 years in the rivers and waters of North America. The name of this creature translates to water dog or water servant. So here's your third clue. This endangered animal is usually black in the wild, but it's white in captivity, thanks in large part to a white specimen being shipped over to France in the 1700s. Do you know yet? Don't worry if not. One more clue is coming up before the top of the hour. On with more questions. This one's for you, Carolyn. This person's wondering, big things get measured in parsecs, apparently. What's a parsec? That's something that that's in Star Wars, isn't it? Han Solo said he could do the Kessel Run in less than 12 parsecs. What was he going on about?
Well, yes, that's infamously wrong, because the parsec is a measure of length, and Han Solo was using it as a measure of time. So that was a big faux pas. But it's a measure of length. It's 3.26 light years, or about 31 trillion kilometres. And it comes from the way we measure distances to stars. So it's using the method of triangulation or parallax, where you look at the way a relatively nearby star is displaced relative to the background when you observe it from one side of Earth's orbit, and then, 6 months and 300 million kilometres later, the other side of Earth's orbit. And if that shift against the more distant stars is 1 arc second, an angular size of 1 arc second, then that star is 1 parsec away. And just to say how small 1 arc second is, as a measure of angular size, that is the size that a pound coin would subtend at a distance of 4 kilometres. So it's a really tiny amount. So parsecs measure distances to stars, but they start to get unwieldy before too long. If you want to think about distances in the galaxy, we talk about kiloparsecs, so thousands of parsecs. So like the centre of the Milky Way is 8 kiloparsecs away from us. Andromeda Galaxy, our nearest large galaxy, is 800 kiloparsecs away. But after that, actually, we use megaparsecs and millions of parsecs. So M87, which was observed by the Event Horizon Telescope, the image of the event horizon around it, that is 16 megaparsecs away. So it's not a particularly useful unit of distance, given that we have to go into mega and kilo quite soon. But it's more, as I say, more historical because of that original way of measuring distances to nearby stars.
If all of the bodies in the universe are in motion, because our star's moving around the centre of our galaxy is moving around as part of a big cluster of other galaxies, how do we kind of keep track of where everything is? Because presumably it's all changing over time, and it's all changing all the time.
Well, now, if you think about modern satellites like the Gaia satellite, who do all this meticulous measurement of motions, they actually use a reference frame which is way external to our galaxy. They'll use the grid of very distant quasars, which are so far away we're not seeing their motion relative to us. So that is a fixed grid that is external to our galaxy.
By referencing that, even though things locally might move around a bit, we've got those fixed points to rely on.
That's right. That's the nearest we can get to fixed points. And, now we can measure things to within about 10 microarc seconds, or that's about the equivalent of your pound coin, not a distance of 4 kilometres, but on the surface of the moon. So Gaia satellite is refining all these distances to fantastic accuracy.
I think Jerry Gilmore said to me it's got a gigapixel camera on it or more, isn't it? I mean, that's some camera. It's eye-watering detail that they're getting, isn't it?
And the amount of data that they get just handling that is a huge challenge.
Thanks, Carolyn. Here's one for you, Liliana, because it says here, let's blow the lid off the Q&A with this question. I think that's probably true. What's the most explosive chemical that we can get?
So the most explosive chemical was made in 2011 in the lab. Never went, out of the lab. It was made in a special chamber, and it's called azidotetrazole. So that's a molecule that has 14 nitrogen in its own structure. And because of these constrained nitrogen bonds, it's very explosive.
Oh, you're saying it's just 14 nitrogen atoms linked together?
Yeah, and it has some carbons in the middle, 2 carbons only. So this is like really a huge amount of nitrogens. And these nitrogens, of course, want to create stable compounds, which is a nitrogen gas. Some scientists said that this molecule could explode even if you look at it, because, it really reacts on the tiniest amount of pressure.
How did they make it then?
So they had a specially designed chamber, which is really, anti-static, and, it can contain huge explosions. And they made a very small amount of grams. And the scientific paper is really funny to read, because every single, figure has the notice, like, this should not be attempted, because every intermediate step is extremely explosive. So this was like just to prove the point that you can make it. But of course, if you would think about commercial explosives, we know TNT is pretty explosive, but actually there is another version similar to TNT, is TATP, which is called a mother of Satan.
Ooh, why?
Yes, so the name is very descriptive. It's even more explosive than TNT and some other explosives. So, pretty interesting stuff. I think chemists actually have always had a little bit of a desire to make the next explosive things. And then, as we all know, nitroglycerin was actually also in some way responsible for Nobel Prizes, because this was one of the first explosives that was made by Alfred Nobel, and he put all the money that he earned by selling this explosive into the foundation that gives the Nobel Prizes. So this is one thing, how explosives can also give something back to science.
Just as well that they did. Thanks for that, Liliana. Here's a question for you, Com. Does physics become unusual at a small scale? It's kind of getting at quantum mechanics, isn't it? So when you're playing around with individual groups of atoms at the scale that you do, what actually happens to them that would be different than if you're dealing with something at the scale that we can see, like a coffee mug or a knife and fork?
Well, there are so many things. I mean, at a very basic level, when you make something small enough, so let's say you take a particle that's just a few nanometers across, you can do a simple calculation. You can figure out how many of the atoms in it are on the surface and how many are inside. And if you think about it, atoms inside a material are surrounded on all sides by other atoms, so they are energetically in stable states. They're in bonding configurations that are low energy and stable, whereas atoms on a surface are not surrounded on all sides. They basically have higher energy, but you also have quantum mechanics coming into play as well. And what that's all about is we think of the world around us as comprising particles and waves. So we think of light as being a wave, and we think of matter being made up of particles that are hard, solid objects. It turns out that that way of looking at things, while it's very intuitive and it makes sense, it fits in what we see every day, that breaks down when you're at atomic dimensions and below. Even things like simple electrons do not actually behave like solid particles when they're moving through material. So when you've got an electric current flowing through something, it's made up of all of these little particles which, under the right conditions, can display wave-like characteristics, which means they have interference. You know, you can get electrons communicating with each other over vast distances because of this wave nature. In nanotechnology, what we're doing is, because we're working with pieces of matter that are just nanometers across, the nanometer is the length scale associated with a lot of quantum effects. So yes, so in order to do nanotechnology properly, you need to understand quantum mechanics, and physics gets very strange. Yeah.
Very strange, very quickly, Com. Thanks very much. Well, I better tell you another clue about our Guess Who mystery guest creature this week, so you can try and work out what this is. Clue 4 is, this creature can regrow limbs, and it can be changed into something closely resembling a salamander if you inject it with iodine. Anyone know? Yes, indeed, it's an axolotl, an endangered amphibian that resembles a juvenile salamander. So congratulations if you at home got that right. Let us know, perhaps by Twitter, and we'll give you some salutations and acknowledgement in the next programme. And let's finish by asking you, Liliana. Yes. We've heard about the biggest threats. What about the biggest molecules? Because this person wants to know, what is the biggest molecule that you can tell us about? You've told us about the biggest bang, so what about the biggest
molecules? If we talk about the synthetic ones, there is the one that was made recently, relatively recently, 2014 in Zurich, and it's called PG5, and it's a kind of polymer generation 5. It's a huge branched polymer that has 17 million atoms. So the scientists managed to create...
Of what?
They have carbon, nitrogen and oxygen in its structure. And if you imagine water has 3 atoms, this is huge.
So what is this stuff, and what would one do with it?
So they wanted to make it because there is a kind of ongoing competition who's going to make a bigger polymer. So, and with using the standard chemistry. So they did a very nice trick where they used all the standard polymer chemistry to make such a giant molecule.
But what's the difference between that and a rubber tyre? Because if I make a huge rubber tyre, that's an enormous polymer, isn't it? So is that not a massive molecule?
It's not actually. It is a polymer, but it's not as huge as you are actually making it.
So it's lots of molecules added together, not all linked up.
Exactly.
Whereas this one they're all chemically linked.
Really linked chemically.
Right.
All the atoms are linked chemically. So they are thinking, because it has a size of a small virus, so it's a 10 nanometer size.
Well, the molecule itself.
Yes.
Wow, it's big.
So they think they will be able to use it for drug delivery, because it has different branches that have different affinity to water. water, these branches will probably collapse and they could kind of create a shield around the drug and then deliver the drug to the cells.
Is it easy to make? Because one of the frustrations with many of these enormous things is they're really difficult to make. So although they might have great applications, they're such a pain to make. We can't possibly scale them.
I agree, but this was particularly interesting paper, a particularly interesting molecule, because they have used a standard chemistry, so it's relatively easy to make it.
Thanks, Liliana. Well, from massive molecules to the fact that we have massively run out of time, thank you very much to our guests this week, Liliana Frucht there, Carolyn Crawford, Colm Durkin and Hayden Belfield. Do join us at the same time next week when we're back onto the science of extremes, when we're taking a deep dive into the science of the extremely deep. And in fact, I don't mean emotionally deep. I've been to one of the deepest mines in South Africa, where they mine gold, and it stretches down over 5 kilometres underground. I went down there and we recorded what I hope will turn into the world's deepest podcast. Join me next week on my journey down, and let's find out how we get on. Meanwhile, thank you for your email, Dominic. You tell us that you've listened to The Naked Scientist and it's helping you to revise for your exams and gather the necessary momentum and motivation. So well done to you. So stop listening to the programme and get on with your revision. Only kidding. Thanks for listening, and we hope it goes well for you, Dominic. The Naked Scientist comes to you from Cambridge University, and it's supported by the EPSRC and Rolls-Royce. I'm Chris Smith. Thanks for listening, and until next time, goodbye.